Hey, welcome back to Math with Patrick. Today's October 4th, and we're solving problem 276 from the Daily Epsilon calendar. And the answer today should be 4 because it matches today's date. And we're also joined by Quill again. He will be helping out with some of the math. Okay, we need to find the ratio of the areas of triangle ABC. That's going to be the big one. And triangle DBE, that's going to be this small one right here. Okay, I guess the first thing that I want to prove is that these two shapes are similar to each other. And to prove that shapes are similar, one thing you can do is just show that their angles are all the same. And so since the small and big triangles both share this top angle right here, I know that this angle is going to be the same for both of them. That means that we have the reflexive property kind of helping us out here. The reflexive property just states that an angle should be congruent to itself. Kind of obvious, but it has a name. The next thing I want to show is that these two lines are parallel. And how do I do that? I'm not quite sure. One thing I'm seeing is that this side and that side are congruent to each other. And so this point right here is the midpoint of this line. And then also this line kind of shares a vertex with this other one here. We also have another pair of kind of congruent line segments. And so this is another midpoint of this line. And both of these two lines join up with the same line on the bottom. And so if this point is halfway down this side, this point is halfway down that side, then I'm pretty sure this is enough to say that these two line segments are parallel. Okay, then now that I have parallel lines, I can find pairs of corresponding angles. I'm kind of thinking in terms of those like parallel lines and transversal problems, where angles kind of in the same spot here and here have the same measurement. And then I can do it on the other side as well, where this angle and that angle are going to be congruent. So that just shows me that triangle ABC and triangle DBE are similar to each other. So I'm using this tilde to kind of represent that they're similar. And now I know that there is some common scale factor that I can use to go between the lengths of ABC and DBE, vice versa. And it's probably pretty clear that like if I take this side and double it, I would get the whole long side. And so the scale factor here is going to be 2. I can use the number 2 to multiply any length on DBE and get the length of whatever corresponding side in triangle ABC. And this times 2 is being applied to all of our linear distances here, not just one of them. Like to draw a different example, like if we started here with DBE and we only doubled one of our side lengths, then maybe it would look something like this instead. And then now we no longer have similar triangles because their angles are all different. But in this diagram, we do have similar triangles. We do kind of apply this scale factor, not just in one direction, but 2, because I'm thinking that like area represents like a 2-dimensional value. And just from this, I kind of already know the answer is 4. Like I don't need to assign any numbers to it. I know that if we have some linear scale factor, which is 2 in this case, and we apply this linear scale factor everywhere in our diagram, the area scale factor is just going to be this 2 squared. And then this is the 4 that answers today's problem. If we had some kind of volume problem, that scale factor would then be cubed to find the difference, or rather the multiplier, I suppose, to go between the original volume and the final volume. But since this is just an area problem, it's just this 4 right here that answers our problem. One more way we could kind of prove that this kind of ratio between the areas should be 4 is just to draw more triangles in this diagram, right? So we can still assume that these are parallel. We can assume that all these angles that I'm drawing right now are congruent. And I am just going to draw the reflection of this top triangle here. Knowing that kind of this point and this point are midpoints, I do know that this vertical distance here and this vertical distance here are also congruent. So when I reflect this top triangle down, I will get a point that lands directly on this line segment AC. And maybe instead of only reflecting it, I think I like reflecting it horizontally, like downwards. I also want to reflect it vertically. And so I still want to keep that DE in the same spot. But then if I move over that kind of altitude over here, my claim is that we now have 4 congruent triangles. And we can kind of test it out. So we know that this side and this side are kind of given to be equal to or congruent to each other. And then this side right here is going to be congruent to itself. It is a shared side between the top triangle and this middle triangle. What else can I do here? Well, I mean, I did just reflect it downwards and reflect it around. So this length and that length should be congruent to each other. And so this is another kind of double marked spot. And then this would be one of our like single marked spots. And so it's the same triangle repeated in all 4 spots in this diagram. And you can kind of see here that we do need 4 of this kind of top triangle of DBE to kind of fill in all of the bigger triangle. So either way, just thinking about it in terms of scale factors or thinking about it in terms of symmetries with the shapes, it's pretty clear to see that we do have a ratio of areas of 4 to 1 because we do have 4 of the little guys in the big one. So I think that's about it. Maybe I might have missed a step or two in like my geometric logic, but either way, I think it's pretty clear that the answer is 4. So I'm feeling all done here. So thanks for watching, and I'll see you tomorrow. Bye.